Yeah, so this is a joint project with Linskens here in Bonn and Luca in Regensburg. And our goal here is to give, in some sense, to make precise an intuition that people have had for a long time about global spectra. So, first of all, what are global spectra? So, global spectra, the concretization of a phenomenon that everyone that has worked in homotopy theory certainly noticed. So that is the G-spectra tend to come in families that are somehow uniform in G somehow. So for example, G-spectra come in families. So as an example, we have a classical one is equivariant cohomology. You have a Brandon cohomology for every G, and they are somehow compatible. Or you can get complex or real topological K-theory. Hence, I satisfy the requirement of having K-theory on the board, which I wasn't aware it was a requirement of the workshop. Easily satisfied, obviously. So you have this, you have, this is the group completion of complex vector bundles, so complex equivariant vector bundles, and these real equivariant vector bundles, and they are in some sense uniform in G, in the sense that, for example, if you have a map of a compact Lie group from G to H, you can definitely restrict an H equivariant vector bundle and look at it as a G equivariant vector bundle. Or other examples are the various versions of cobordisms, which I think are called like this, with the one with a little m and one with a big M. I never remember which one is cobordism and which one is stable cobordism, but we have these two families of G-spectra. And there are, oh, I almost forget, there is, of course, algebraic K-theory of representation rings. That's also, we've seen, it's an important family. And so, as you can see, we have a lot of examples of stable homotopy objects that are somehow varying in the group. And the global spectrum is a way of making precise what this gadget should be. So, to start, I'm going to introduce a category that was already introduced by Leonard, but let me be a bit more precise. And this is, well, I'm not going to be fully precise either, but at least I will tell you what the mapping spaces are, instead of the same in words. No. And this definition, I think, is due to Gepner and Gepner and Linskens, sorry, I think. It's a bit hard to navigate the literature sometimes, and try to attribute as much as I can. Sometimes the same things come with many different names, and in fact I will use a different name from Leonard just to keep you on your toes. No, I'm kidding, I have a reason for that. And this is the category glow, which is what Leonard called orb, I think 2 days ago. So this has objects are, let's see, let me go here. Objects are compact Lie groups. V. And morphisms, well, you maybe want to take, so map below GH. You maybe want to take the space of Lie group homomorphisms from G to H with its natural topology coming from the fact that G and H are topological groups. But that's not all what we're doing, because there is a residual conjugation action on these by elements of H, and we take the homotopy orbits of this action. Well, this is an infinity category. This is not a full definition, of course. I haven't told you precisely how to define composition and the higher coherences. And the way you do, the way I like to do it is to consider it as a category enriched in topological groupoids, which you can just write down, and this gives you a category-rich and simplicial spaces by taking the corresponding bar constructions, and from that you can get an infinity category. Okay, and in fact, I mean, this action is very, very nice, so it's not a drastic operation. And in particular, as an example, if G and H are finite, this space here is just the groupoid of group homomorphisms alpha from G to H, where we have maps with maps alpha to conjugation H on alpha for every H in H. So these are the kind of maps we have. We just add a map for any, so it's the action groupoid. And in the case when there are complete groups, you also have a topology which I'll completely ignore in this talk, but it's there and one actually has to take that into account. Okay, so
one thing, but important, only the CH is important, not H and H. You know, when H is
no, H is important. Sorry. You have to remember the H.
Because I've looked at the other categories, but where you divide all the centralizers, and they don't play a role, but here they play a role.
Yeah, they do play a role. That's very important. Yeah. Thank you. In particular, this category glow this has a subcategory, or inside of glow, which corresponds to injective group homomorphisms. And this is well defined because being injective is stable under conjugation, of course. And then this is all set up so that if there is an equivalence, so in fact this was already implicit in Glutamine and request, then it's been proven in different contexts by different people. But I think this formulation is with Charles Resk, and there was a proof by David Gepner and Lennart, and we give yet another proof in our paper, that there is an equivalence from R over G with the topological orbit category of G. So this is the category of transitive G spaces and equivariant maps. It's seen as topological category, so you can identify the infinity category. So you have this. In particular, you have a map of G mapping to glow. And so you get a map, in some sense, uniform in G. Oh, sorry, I didn't tell you what this map is, actually. Let me be. This more or less sends the orbit G mod H to the map H goes into G. Now, this is not well defined the way I've written it, but you can make it well defined with some effort. And this remembering H is actually the key in making sure that this map is well defined. Okay, so you have a map of G to glow, which morally is sending G mod H to H. Again, this is not well defined as it stands, but it can be made well defined. And so you get a map from pre-sheaves, spaces. So I'm going to write this calligraphic S for the infinity category of spaces to the pre-sheaves over the orbit category, just a pre-composition. And this is, we know by Eldendorf's theorem, this is just the infinity category of G spaces. That is what you obtain if you take topological spaces with a G action and you invert the G-equivariant homotopy equivalence. Weak homotopy equivalence. Okay, and so we have this sort of universal map, and due to this reason, we can take, I think it's the definition, the original definition by Gepner and Enriquez here. There have been other models due to many people, but we can take this as definition of global spaces. So this is something that remembers a G space for every G plus coherence data. And the goal of this talk will be, let's make precise what these coherence data are. And what are these good for? Well, one first remark is that all of these cohomology theories that I wrote there can actually be encapsulated into a functor. So suppose you have a functor from a pre-sheaf, let's say, from global spectra, global spaces to spectra, then you can get a what I like to call a Braddon, some people call naive, cohomology theory on G spaces just by precomposing with, oh, I forgot to say one thing. Sorry, this map has a left and right adjoint. And what I'm taking here is the left adjoint, which is usually defined, called the Orbi space quotient. And everything is very explicit. You can see it's basically a combinatorial game. You can write down what these things are. And it turns out that all these cohomology theories here are obtained from a global cohomology theory here under this process. And one way to get intuition is that you can actually see these global spaces as differentiable stacks up to certain weak homotopy equivalences, so inverting certain homotopy equivalences on differentiable stacks. And for example, equivariant K theory is coming from the K theory of differentiable stacks. That's not the only way of constructing this. But okay, so if that's all we had, I mean, we say, okay, well, that's fine. I mean, our job is done. The book is finished. But actually, I am hiding something that all these gadgets here are not just what we call Braddon cohomology theories, or something more. That's what we call genuine G-spectra, which just intuitively means they have the Thom isomorphism for oriented equivariant vector bundles. And well, the cohomology theory that's described in this fashion in general does not. So we would like to, package this additional bit of information. And that's the reason for the definition of global spectrum. So I'm going to define global spectrum in a minute, but first, are there any questions about this?
Yeah, these theories are always confused. This extra structure you said comes from the restriction, but there's also induction. You can go from KOH to KOG by induction. You can restrict, and you have a Mackey functor. Is this also encoded?
Yeah, that's not obviously so, but it is equivalent to having the loopings for all the representation spheres. So being like what we call a genuine G spectrum, and that is additional. That's additional information. At least for a finite group, it's easy to see. I mean, for a non-finite group, the precise statement is not quite known, I think, of what transfers are equivalent to the loopings. Although I do have suspicions, but maybe I won't speak about them. But yeah, that's exactly the kind of additional structure we want to encode here.
No, for infinite groups, I would expect that you need sometimes some finite index subgroup.
We can talk later about speculations. I don't know. I actually expect you need some kind of frame transfers, like in a motivic setting. But
for instance, for algebraic K theory as well.
Well, an algebraic K theory should not be relevant to the frame. The framing should be ignored. But
okay, great.
But this is speculation, and I'm not comfortable in asserting anything.
Okay, sorry.
No, it's a reasonable question. It's a question many people have asked, but. At least for finite group anyway, that the looping is exactly this push forward. Okay, so let me give extremely briefly the definition of global spectrum. We will go back to that in a second, later when I'll talk about the proof of the main theorem, but just for the sake of having it on the board, so we can start with orthogonal spectra. Pick whichever definition of orthogonal spectra you're comfortable with. I'm going to see it as a one category, and sorry, I should do this as Stefan here. So let a map x, y of orthogonal spectra is a global equivalence if it is a G-equivariant equivalence, a stable G-equivariant equivalence, in the sense of, say, Mandel-May or whatever your favorite reference for G-spectra is. I'll say more about the details later. Stable G-equivariant equivalence for every G. And here I'm seeing X and Y as orthogonal spectra with G action just by endowing them with a trivial G action. And I'm also using the observation that, for example, the Mandel-May model of orthogonal G spectra is just equivalent to orthogonal spectra with G action. It's not completely obviously so, but it is. So we are allowed to say this. And then we define global spectra as taking orthogonal spectra. So this is my symbol for the category of orthogonal spectra. And we invert global equivalence. And again, I'll possibly go more details into this construction later when I will compare it. And the intuition, as far as I can tell, it's always been that a global spectrum should be the datum of a genuine G spectrum for every G plus compatibility data. For example, you get, just by definition, you get a map from global spectra to G spectra for every G. Just by taking orthogonal spectra, including them in orthogonal spectra with G action, by endowing them with a trivial action, and then this passes through localization by definition. So you definitely get, if you have a global spectrum here, you get a family of G spectra. And again, all the examples I put on the board there are actually, all these families are coming from such an object. Yeah, I think. Yeah, and you also, as Lennart has explained that, we also have a TMF family there.
And for the algebraic case, you need to restrict to finite groups.
I guess, yeah, for algebraic case. You can also do this restricting to a family of groups. And I guess algebraic case theory is not only for finite groups.
I wouldn't know.
Oh, defined only for finite groups, yeah. It's not clear what R brackets G means for non-finite.
So is there a global spectrum model for the design global T2 is the Stone's K theory?
That's probably what he means, because algebraic K theory has the wrong functoriality. Algebraic K theory of the grouping has the wrong functoriality.
Oh, wait.
It must be meaning Swan K.
Swan K theory, yeah, I guess I meant that, yeah. I meant the object constructed by Tobias Lem, is it?
Which is yeah, it's like underlying finite project.
I mean, if you want it to be a global spectrum of finite groups in this sense, then this is in my paper on global algebraic K theory. Tobias extended this to an additional G action outside.
Oh yeah, right, you have a G global spectrum. Tobias did a G global spectrum, right. Anyway, yeah.
When you say Swan theory, you mean direct sum K theory?
Yeah, so the G fixed points are the direct sum K theory of R projective finitely generated RG models.
Yeah, sorry, I meant G representations, I guess, instead of RG modules, which are not quite the same thing. But, okay.
And I mean, for compactly, that still makes perfect sense, but you say it's not global? Or it's
I guess it's not known to be global, but...
And what modules are you considering then?
Just functors from BG to perf R. As an infinity category, it's K theory.
I guess it's not known to be global.
But, up to this paper, the issue was if you wanted to write down a global homotopy type, you had to write down one categorical model. I couldn't.
Yes, it has.
Yeah,
I think now things might be
this paper, the result I'm about to say, it might be easier.
There are many things where you have families of compatible spectra and you'd like to say this is a global spectrum, but so far you have to write something down.
But okay. And
you still have to write something down.
Okay. But okay, the intuition is that the datum of a global spectrum, as I said, should be the datum of all these EGs plus some compatibilities. And to make precise what we mean by some compatibilities, I'll need a categorical digression. Now, what this means. So, this is partially Lax limits. So So I was hoping against hope that Lax limits would be defined yesterday, but apparently they weren't. So the job falls down to me. So let's start first. So I is an infinity category, which actually in all our examples will be either glow or glow up, but let's be general for a second. The question is, what is the datum first of a functor from I into cat infinity? I will sometimes forget about the infinities. I hope you can bear with me on that. Well, let me give you, of course this is an infinite amount of data, but let me give you at least the first places in the list so that we can understand. So we have for every, let me call it C actually. For every I in I, we get an infinity category Ci. That's uncontroversial so far. For every F from I to J, we get a map from Ci to Cj, and this is going to be, let me call it F lower star. That's a functor. And then, but that's, so if we had just the one categories here, we could stop and say, okay, then we ask just compatibilities, but since we are infinity categories, you have additional structure. So let me just give you the next level. So for every homotopy, from F to F prime, homotopy means a path in the mapping space. So I can write down the following diagram. Homotopy. Oh no, okay, yeah. You get, sorry, no, the diagram comes later. I get a natural equivalence, which I'm going to call H lower star from F lower star to F prime lower star. And then there are additional data that ensure that this continues in some sense. And okay, suppose we have, and I guess I'm going to go to the next board for the space reasons. So suppose we have such a gadget, the question will be, what is the limit of such an object? And let's see if I. So when I came here for the workshop many years ago, I was totally unable to use these gadgets, but now I've lived in Germany for a while, so I should have learned how.
You're just building up pressure on
It's slightly different from the one we have in Regensburg. In Regensburg we have two pieces. This is more technological somehow.
And remember, this is recorded, so everybody can check it out.
You check your progress.
That's a D, okay? That's a D.
No, I don't. There is.
Wait for that.
Right, I have to do it this way. Right?
You're doing a good job, Dennis.
I think that's okay. What you don't know is that I was at a conference in Essen a few months ago, and I encountered one of these, two pieces in one gadgets for the first time while I was giving the talk, and I was utterly flabbergasted. But now I'm prepared. Anyway, sorry. Where was I? Yes. So now we want to ask the question, okay, what is the limit of Ci I in I? And I'm not talking about the formal definition that we have seen yesterday, but I'm talking what kind of object is this? So one way of computing this would be, the recipe, classical recipe is use unstraighten C to a co-Cartesian, fibration. So we do the Grothendieck construction, in other words, like this, where the objects are just pair of an object in I and an object in Ci, and maps are, as you can imagine, and a lot more work goes into defining precisely what this gadget is, but it's been done, so ignore, and take the category, the infinity category of sections xi to the Glutamine construction, sending every arrow to a co-Cartesian arrow. Okay. And concretely, what does this mean? This means, so we have for every I an object xi in Ci, and for every arrow f from I to j, we get a map, an equivalence, f lower star xi to xj, and then call this, what did I say to call it? I think I'm going to call it epsilon f. And just for fun, let me see what the next step in the power gives us for every homotopy f prime. So I can write such a diagram. I have f lower star xi, this maps to xj with an equivalence. I have f prime lower star xi, this is epsilon f, this is f prime epsilon f, but I also have that natural transformation. And what I have to give is a homotopy here of these two maps. And then you can have fun and write all the higher coherences that I want. But since we are going to have important two cells, I think it's important to see what they mean. Yes?
Sorry, I have a nasty question. So is unstraightened something model independent or does
It is. It is model independent.
Okay, then I'll ask you afterwards.
You can just pull back the universal co-Cartesian vibration which exists sort of.
For example, that's possibly not the easiest way to think about it. But yeah.
Well, that's good enough. Thank you, Mark.
Anyway, okay, so that's the limit. That's what an object of the limit is. But note that here we have arrows, but we ask them to be equivalences. And the lax limit is what happens if we forget that these arrows are equivalences. So definition, the lax limit I in I, Ci is the just the infinity category of sections. I goes to the Glutamine construction, and concretely, this means that I don't ask these arrows to be equivalences anymore. So I have an object for every xi, and a map epsilon f for every f, and they satisfy all these compatibilities, and I still ask this homotopy to be invertible because, well, homotopies are always invertible, so it's fine. And for the purpose of this talk, I need a slightly more general notion. So suppose I comes equipped with some kind of subcategory, which in our case will be, I erased it, but remember we had glow and we had orb inside glow on the injective maps. Then I can ask for the partially lax limit, which is just the limit that is lax only away from x dagger. Lax limit that is required to be strict over x dagger. There are many ways of saying this, but I can say an infinity category of sections I to this Glutamine construction that send arrows in x dagger to co-Cartesian arrows. For example. And and that's the lax limit. And let me put a remark here. That is essentially, an observation about lax co-limits, but I don't want to use those words since we already have enough category theory on the board. So I'll just say that if you have a map, suppose you have a functor from I up into cat, this time, and a category cat infinity, and then in another infinity category D, you can ask what is the lax limit of fan C dot into D. Right? Because, just applying functors into D, giving a contravariant functor, and so on. And this is fairly easy to see from this definition. It's just functors from the Glutamine construction into D. And that's actually the fundamental categorical input we will use in our proof. It's just essentially true by definition with these definitions I gave. If you prefer other definitions of the Lux limit, you have to prove it, and then it's equivalent to showing that these are okay, so now I have all the categorical nonsense I need. Well, that's actually false, but all the categorical nonsense I need for this talk. Yes?
You said proof of what? You need it for your proof.
I need for the proof of the statement I'm about to give.
There was no statement. No?
The statement is not on the board yet.
Sorry. I thought they had to list something. Possible.
No. But that's, I want to say that this is essentially all the categorical input I will need for this talk.
Single atomic spectra is a Lux limit, is that right?
Sorry?
Single atomic spectra, it's a Lux limit.
It's a partial Lux limit because unfortunately what you might want to call a Lux pullback is not the Lux limit over a pullback diagram, it's a partially Lux when you mark one of the edges. And this explains why it has a directionality, because you choose which of the edges. And there is also, you might notice that I always use co-Cartesian fibrations. There are also a notion of Lux limit using Cartesian fibrations, but that will never come up. So, okay. Now, when is it? Okay, now I'm doing well on time actually. So, let me give the theorem. Linskens, myself, and Luca Paul. So, we like to write it in two steps. Even if the first part was already observed in the past by other people, but we give a different proof that's important for the second part. So there exists a functor blow up into cat infinity, sending G to the infinity category of gen G-spectra, and actually a map G to H is sent to alpha upper star, so it's the restriction when alpha is injective, the inflation if alpha is surjective, but it's still the same map. I mean, they just have different names and composition if you want, if you have an arbitrary map. Okay, and you can actually say something more, you can be much more explicit about what this functor is, but let me leave it for the proof in case. Oh, sorry, and there is also another one. It's a lot easier to construct, so I forget about it, but it's also, well, there is functors. There is also one getting G spaces. And then the second part is there exist equivalences from G global spaces to the partially Lux limit, so G in glow up of G spaces, where glow is marked by orb, as I said before. Technically I should put it in the notation, but it gets rather involved already, so I'll drop it. And same thing for G-spectra. Glow up G-spectra. So what does it mean? It means that I keep a global spectrum is the datum of G-spectrum EG for every G, a map alpha per star EH to EG for every alpha from G to H. Here alpha has got upper star because we have this controvariance in the group. Just a harmless piece of notation. Okay, we have a map which is an equivalence whenever alpha is injected, but not always. Only when alpha is injected. And just for the sake of concreteness, let me tell you what the other diagram tells us when the homotopies are these homotopies from alpha to the conjugate of alpha I mentioned before. And for every G in G, a homotopy, so sorry, this encoding is F alpha. A homotopy between FCG, so this is F for the group homomorphism from G to G given by conjugation, and this is G lower star from E, from CG upper star of E, EG to EG. So this, if you want, this is the map on spaces, is just the map multiplication by G and gives an equivariant map, in fact an equivariant equivalence from the twisted action by the conjugation. So this is of course more general, but if you unravel what this homotopy tells you, is essentially tell you that there is such a homotopy between this map for the conjugation and the natural map we already have for the conjugation. And then plus compatibilities. So that is, I think, a relatively intuitively description of what a global spectrum should be and makes it precise. It's a G spectrum for every G plus Glutamine data. Yes?
This might be a bit pedantic, but sort of the way you formulated it seems a bit awkward in the sense that you're saying that there exist functors. Yeah, I suppose what you mean is they induce these equivalences?
Well, no, the functors are going to be the Lux limit.
Yeah, but
there exist, the equivalences are actually pretty natural, and actually I should say, for example, here if you project to one of the components, you get the natural map. You have to say, I mean, this thing has also these equivalences are compatible with sigma infinity plus, for example. There are all sorts of compatibility that.
Can you somehow, make the functors in part one, I don't know, in some sense unique, or
well,
more than?
Let's say that this first functor is uniquely determined by the second one.
Sure.
So you have, and that's already the second one. I'm not sure if I can make it unique in any sense. It's also a very natural functor too.
But if you had any other such functor, you could also take this Lux limit. Does 2 depend on?
No. This is proven using these functors. That's why we reprove these, because we have a different model for these functors. In particular, a different model for these that doesn't come from the universal property that is essential in the construction of these equivalents. Then, of course, since this functor has a universal property in terms of this functor, this has to coincide with all the other constructions. But
the one issue is that global spectra are defined by a one-categorical model, and the full functoriality in alpha is actually difficult to come by in this model. So the best you can sort of hope for is point-wise identifications, and then with a functoriality up to homotopy or something. And that's what you say. The one-categorical model doesn't really initially have this continuous functoriality. At least it's not so easy for me to see how it would have it.
No, but I guess the question was if this functor is.
Well, relative categories.
Okay.
Category for global spectrum and global equivalences.
Okay,
Okay, so yes?
Is there a relationship between the Glutamine construction of the orbit category and the global category? I'm trying to apply that formula.
Yes. although that's less deep than you might think, because the factoriality already has the global category inside. So when you build the Grotin construction, it already maps to the global category. But I think I want to give you the complete proof for this case, which is easier, and then you will see exactly how that works. And then maybe I'll say a few things on how you try to adapt. There's a lot more technical details to go from this case to this case. But other questions about this statement?
Yeah, maybe one. You see, I have a look, this is a very naive point, because I was taking homotopy groups some time ago. The other thing was that they have found the from groupoids to spectra. You get something, because your orbital category maps into the groupoids, which automatically has this kind of global structures, but in a naive sense. I think Stefan knows what I mean. Is something like here as well, that when you have a function from groupoids to spectra, you get something global out of it?
I'm not sure.
Naive global. You don't get genuine homotopy types.
Naive global means in.
I mean, just a function from glow to spectra that you get.
Okay, but that's all. Because the transfers are not there.
I mean, yeah, maybe I'm not sure I want to say anything at the end, but there is a question of what does it take to extend from such a, maybe I guess I want to call it random global, I don't know, but my more preference is in notation, but to a genuine global object. And it's very related to constructing a global model for TMF, for example. And the question is exactly what you need to add. And let's just say it's still a matter of active research, exactly what universal property, so to speak, global spectra should have.
Because when you wanted to look at algebra Casey or System algebra, you just have this groupoid function, but not more. But don't worry about this.
Yeah, I know.
That is Casey, right? If you take group ring Casey, it has the wrong function.
Yeah, probably. Yeah, because you do this one.
This is sort of an op-global spectrum, which in one categorical models I wouldn't know how to define, but here you just
You want what?
an op-global spectrum. If you take the algebraic Casey or the group ring.
Oh, okay.
Which I wouldn't have a one categorical model for what that means, but I guess now infinitely higher categorically it's the same.
Okay. Well, okay. So, okay, what's left of the talk in the remaining 15 minutes, I think, I want to give an idea on how you...
Oh, actually 5, 6, 7 say, because I started late, it's 15 minute talk, so 7 minutes, yeah.
Oh, 7 minutes, yeah, sorry.
Yeah.
Okay. At least I want to give you an idea of the unstable case, maybe the stable case. But, okay. So the first idea is how do we define this functor? So to do this, we apply the Elmendorf's theorem that we identify genuine G spaces with pre-sheaves on the orbit category, and we construct, in fact, a functor from glow, this time not glow up, into categories, sending G to the orbit category. And this is done the way you always do things in infinity category, when you have these very complicated objects with a lot of coherencies and it's hard to define things, you get a vibration instead. And so, and you use the fact that this is in fact orb over G. So we take R inch G, glow, sorry, up, and you map it into glow up via the target map. And this turns out is a co-Cartesian vibration. And this requires actually, this is actually the key point of the proof somehow. You have to prove that this category glow has a factorization system where every morphism can be factorized as an injective followed by a surjective. Now if you just took the category of Lie groups, that would be obvious. But here we have additional two cells, and it turns out however, that the same argument works. And indeed, you have this factorization system, and this gives you that it's a co-Cartesian fibration with fibers of the form orb over G, fiber over G. This is because I'm restricting to injective arrows. And you have to be a bit careful that the morphisms is given by induction, it's not given by restriction, of course. Otherwise we would get the wrong functoriality. So a morphism sends, so if you have G to H, this sends G mod K to G, H mod alpha K. Okay? And the reason why I want this factoriality is that precomposition by these objects gives exactly the restriction in G-spectra, as was observed many times. And, okay, so then I can do the same trick as I did before. So this gives us a functor, like this, let me call it O dot. And so I get a functor.
Sorry, I'm confused with ops. If it's a co-Cartesian fibration, you get something from glow ops.
Oh, yeah, sorry. You're absolutely right.
Yeah. Okay.
Yeah. You are absolutely right. Sorry. What I want to say. No, wait. Oh no, sorry. That has to be a co-Cartesian fibration. I mean, it's both Cartesian and co-Cartesian, but I mean, I guess the question is.
I mean, how do you straighten it or straighten it?
But I mean, because
this function is covariant.
This variant is covariant, so I guess I want this.
When you're gonna home this.
Oh no, sorry. That's the point. That's the point. In fact, first of all, I have to put the up inside. Not that it matters much.
But then aren't the fibers of the target map still something like?
Yeah. Okay. I guess I want to do some kind of fiberwise up. The point is, I have this functor here, and then I can get a functor O up dot into spaces, which is the real functor I want. Yeah. And this is my functor S dot that I define. I'm not sure there aren't that many ways of getting this full functoriality in Glow. In the classical technique, there are a couple, but they're all basically the same trick, more or less. I'm not sure if there is a way of getting it like one categorically, because this category Glow has a lot of hints. Anyway, then I can use the same trick as I did before, and now I'm worried that only for the purpose of this talk I am getting some ops wrong, but for the paper we check them extremely carefully, so no matter what happens here, the result, I'm confident in the results of the paper. So you can ask what this is, and this, by the argument I sketched before, this is, sorry, not daggers. This is just functors from R inch Glow up into spaces. So that's just the Lux limit, and that's just in some sense categorical nonsense. And now the question is, okay, but I didn't want these. I wanted the dagger, the partial Lux limit. And it turns out that you want to see what sections here send arrows in orb with co-Cartesian arrows. This boils down to sending certain of these arrows to equivalencies. Precisely arrows that are equivalencies on the source are sent to equivalencies. And the final remark is that these maps are in Glow to Glow, given by the source map. Sorry, the target. Well, there is confusion with ops, unfortunately, but the first remark is that this is a Bausch localization. This is a localization as it has a fully faithful adjoint. Given by the identity arrow. And so therefore, inverting arrows here corresponds just to taking Glow up. So the Lux lim dagger SG, G in glow, is just functors from glow up into spaces, which is by definition global spaces, at least in the model I took.
And I mean, I have to check that. I mean, it's a localization at exactly these.
Yeah.
coefficient over the
Yeah.
Okay, I see.
But everything is super explicit, everything is straightforward, so it's for lack of time, I think I don't have any more time, and so I'll say just that there are some more complicated arguments you have to do for global spectra.